Good afternoon, and welcome to our presentation on building better structures to withstand the effects of earthquakes. To start, I'd like to pose a question. Why can two earthquakes of the same magnitude have such different effects of infrastructure?
Before we begin to answer this question, let's first explore the different types of waves that occur during an earthquake. These waves can be split into two main categories, body waves and surface waves, which can again be split into subcategories. There will be an animation in the top right corner so you can see what each wave looks like. Body waves consist of P and S waves. P waves move much faster than S waves and oscillate parallel to the direction the wave is travelling in. S waves oscillate perpendicular to the direction the wave is travelling in, which is why they can only travel through solids. Surface waves consist of Love and Rayleigh waves. Love waves also oscillate perpendicular to the direction the wave is travelling in, however only on the surface of the Earth. Rayleigh waves oscillate in a circular motion, similar to a wave in the sea. In general, surface waves tend to do much more damage than body waves.
There are two types of scales used to measure earthquakes. The first and more well-known one is the Richter scale, which measures the intensity of an earthquake at the epicenter as it happens. It's measured logarithmically between 1.0 and 10.0, so this means that an earthquake measuring 8 is 10,000 times more damaging than an earthquake measuring 4. Less well known is the Mercalli scale, which measures the effect an earthquake has on people based on opinion. So an earthquake could be quite high on the Mercalli scale, whereas quite low on the Richter scale. So as we've said, the higher an earthquake is on the Richter scale, the more damage it causes. However, we did find some examples where this wasn't quite the case. So in 2010 in Haiti, there was an earthquake measuring 7.1 on the Richter scale. It killed more than 220,000 people, and being an LEDC, a less economically developed country, the earthquake, the infrastructure was unable to withstand the effect of the earthquake, so buildings disintegrated. However, in 2016 in Old Iliamna, Alaska, an earthquake that also measured 7.1 occurred, but it caused only moderate damage and no deaths. Being a more economically developed country, the infrastructure was able to withstand the earthquake better, and less damage was caused.
There are many ways to modify building in order to reduce the amount of destruction caused during an earthquake. The most common type of earthquake-proof structure is base isolation. However, these measures can be quite slightly costly and requires many skilled engineers, hence why there's only a small portion of buildings worldwide have this in place. But base isolation is not installed in every building because, one, it becomes less effective for high-rise buildings, and also it's unsuitable to have it on buildings rested on soft soils. Base isolation is where the building is raised off the ground on a flexible bearing made of lead, rubber, and steel. This means that the building is not in direct contact with the ground, and so will shake less violently during an earthquake. Therefore, base isolation is frequently installed under residential buildings, bridges, statues, monuments, and buildings of historical importance.
So, in order for us to better understand the techniques used to create earthquake-resistant structures, we must understand something called natural frequency. In scientific terms, natural frequency is the frequency at which an object will naturally vibrate without dampening or interference. But without all that jargon, it's basically the frequency which the earthquake must near in order to do the maximum damage to the object. Natural frequency depends on multiple factors. For instance, it depends on the stiffness and the mass of the building, but it also depends on the dimensions. So a taller building will have a lower natural frequency, and likewise a shorter building will have a higher natural frequency. A good way to understand this is with boats. If you have an ocean liner out on the water and there's large, low-frequency waves, there will be a lot more sway to the ocean liner than there would with a small boat. But if there's small, high-frequency waves for the large boat, it won't sway half as much as a small boat would. This applies to the buildings. So, for example, a tall building will sway a lot more with a longer frequency of earthquake, which means that it will do more damage, whereas vice versa, with the smaller building, it will do more damage with a higher frequency earthquake. So this allows us to, based on the geology of the area, it allows us to change the natural frequency of the buildings in order to ensure minimum damage is done.
Seismic retrofitting is done in many different ways. It's kind of dependent on budget and whether you need a long or short-term solution. Fibre reinforced polymer jacketing comes in two different types. Concrete filled steel jacketing and epoxy filled fibre reinforced polymer jacketing. The epoxy one is more of a long-term solution because it's more reliable over a longer time. This is because the intermolecular bonds are stronger, and therefore the concrete filled steel jacketing is less reliable. However, it is cheaper. So if you were in an LEDC and looking to install seismic retrofitting, you'd probably use that, but as it is cheaper. In general, seismic retrofitting relates to natural frequency, and it's kind of dependent on the type of retrofitting you use. In general, it just hires the natural frequency.
So now we get into the horrible mathsy stage of, this was the worst bit of the whole thing. We were given formula on our brief. This brought in a whole new area of maths which we hadn't done before. It included differentiation, matrices, a little bit of vectors. But now, after long, painful months, we understand that there, x double differentiate, is the acceleration of the earthquake. A would be the matrix, and x is the vector of the two speeds in different planes. As you can see by the well-drawn diagram, acceleration is proportional to force. And then we were given another equation for the time of the earthquake. This one included something which we hadn't even heard of, called eigenvalues and eigenvectors. In short, an eigenvalue is a scalar for a vector which goes through the point 0, 0, or the origin, and it can be found from an n by n matrix. So in this equation, lambda there denotes a negative eigenvalue for the matrix A, and t is the time of the earthquake. Now this goes back to natural frequency. It's an equation which we found online, we weren't given in our brief. It essentially helps us calculate the natural frequency of a building, not taking into account the height of the building. So F here will be the natural frequency, K is the stiffness, and M is the mass. And you have 1 over 2 pi because a sinusoidal wave has a periodicity of 2 pi. So when you multiply the natural frequency by any time period, it allows us to find a specific time frame in the oscillation.
Okay, so as another part of our brief, we were given the task of finding out whether earthquakes could be modelled mathematically. And so we spent quite a long time researching into this, and it turned out to be extremely complicated. So as part of our research, we found a program called OpenQuake Engine. What this did was it took data from a catalogue and then used that to formulate models so that you could tell where high-risk zones were and low-risk zones were. So in this diagram here, you can see that this area here would be a more high-risk and area where there's more seismic activity, whereas the blue region's less seismically active. Now, we ourselves actually, this is a diagram from the internet. We tried to use this program, and it turned out to be too complicated for us. It requires a ludicrous level of knowledge of earthquakes. On the other hand, though, we were able to do this. So this models a specific part of an earthquake, which is the aftershocks. So after a main event, what will normally happen is you'll have a series of aftershocks, and the frequency at which these occur can be modelled using Omori's law, where in this formula, K is the productivity of the series, C makes up for missing earthquakes from a catalogue, which you'd use to get the values, and T is the time, normally in days after after the main event, and P is the rate of degradation of the aftershocks. As you can see, it creates a pretty standard graph, which you'd kind of expect.
Right. Overall, in order to build stronger, more earthquake-resistant structures, we need to have a thorough understanding of the natural frequency of a building, the type of soil it's built on, and the depth and strength of the earthquake. This can all be calculated using mathematical models. However, these require a vast amount of data to work correctly and predict the damage that might be caused. We would like to thank Dr. Aileen McGregor for setting us this problem and our mentor Tanya for helping us with it. If you have any more questions, you can see us at our post in the foyer. Thank you for listening.